Can everybody hear me up there? We're good? All right. I see a lot of people are missing today, so we're going to take So last time we talked about selection. We said you can select in expected linear time if you do sort of the analog of quicksort. You partition around some pivot, put everything below you to the left, everything above you to the right, with respect to the pivot, and recurs on the correct portion, and the average case is linear, but the worst case is quadratic. And then we gave a much more clever, sophisticated algorithm about the worst case median. That involved partitioning groups of 5, taking the median of the medians, using that as a partition with another level of recursion and all that. Any questions about any of that? How many understand this algorithm perfectly? Okay, that's good. More than half. I'll take that. So let me ask you a question about this. Why do we use 5 rows? Why not use 7 rows or 3 rows or 4 rows? Why are we using 5 rows? What's so magic about that?
Well, 7 can work if we use less rows. If we might change the math of our recursion, and we might get converging 100%.
Yeah, so 7 rows will work. Any number of rows will work bigger than 5. 6 or even numbers will create a bit of an asymmetry because the median of 4 things, it's not clear, what it is exactly. It's 5, it's always the middle guy, assuming they're all unique. So it's better to use an odd number for symmetry and this ambiguity. And 7 would work. 3 won't quite work for the analysis. If you use 3 and do the calculation, you'll see that you don't quite get to 30% in a way that enables you to make this recurrence analysis work to linear. You might get something super linear. So 3 doesn't quite work for the analysis so easily. It'll still work in practice, but the theoretical bound is not guaranteed. Also, we mentioned that there's a very large constant in this, and as you can imagine, because it's double recursion. It's not just recursion in one way, it's recursion in 2 different ways, which each level gives rise to yet more recursion in 2 different ways. And you're computing the mean over and over and over again of subsets that overlap. It's not unique subsets. How do you understand that? Because you're doing the median of the medians, and then the median of the entire set, using the median of the medians as a pivot, so the same elements get swept into the recursion over and over and over again at different levels, which is interesting. So we're doing a lot of extra work in subsets. Okay? But it all works out, as we saw in the analysis. Any other questions about order statistics, sorting, median finding in linear time? Okay. And once you have a median finding algorithm in deterministic linear time, you can use it in many other things as a subroutine. For example, you can use it inside quicksort to pick the pivot inside quicksort being the median, and then it will give you an even split, a lot like merge sort. And then you'll still be enjoying the fast expected time of quicksort, but you also gain the maximum worst case behavior of n log n of merge sort or any other n log n sort. Yet you're still doing quicksort, you're just using this subroutine to get you the median. Now, that's theoretic. I'm not saying you should all rush to do that when you implement quicksort, simply because there's a large constant overhead in this kind of an algorithm, but it's very elegant, and it gives rise to a whole bunch of other algorithms that kind of work in a similar way with kind of multiple levels of recursion and surprising analysis that converges to linear or something very close to linear, even though intuitively you don't quite expect that after doing all this work. And we still don't know the exact bounds from linear, for median findings in terms of the exact number of comparisons. That's still an open problem after all these decades, after 50 years of research. But we do know there's a series of results that kept pushing the upper bound and the lower bound on the exact number necessary for median finding in the worst case. And we know it's somewhere between 2 and 3, basically. We just don't know exactly where it lies. And anybody can narrow that even further, that's probably a PhD thesis right there, in theory. Okay, any questions about any of that? Yeah.
So that large constant overhead, so how much exactly is that number? Is that number also a function of n, or that large constant overhead is just a number?
Yeah, so that constant that we mentioned right here, it's an artifact of the notion that you keep running the median over some of the same elements over and over and over again, and it's double recursion. Every time you recurse this large constant overhead, the compiler always unrolls recursion into iteration, right? I mean, really, there's no such thing as recursion at the hardware level. It's all iteration. So in converting the recursion to iteration, the compiler has to allocate stack frames every time you make a clone and copy some local variables and do some housekeeping work and allocate some frames for the for the call. And then on the way out from the recursion, he has to deallocate it. The compiler has to make sure it's garbage collected or whatever, so it doesn't get out of hand. All that adds up in the constant overhead. And here it's even worse because it's double recursion. And there's a lot of work in between recursive steps. And I mean, even finding the median of 5 things is not completely trivial. It's a bunch of nested ifs, or maybe you run bubble sort on those 5 things. That's yet more overhead. Anyway, there's a lot of sources here of constant overhead contribution to the overall runtime. But you can kind of optimize a lot of it. You can still end up with some of it, And there's a threshold where this kicks in and gives you benefit, just like quicksort. Quicksort runs fast. That's why we call it quick sort, not slow sort. But the catch is, if you want to quicksort just a few things, like cards of a poker hand, don't use quicksort. Don't start recursing in the middle of a poker game. You'll probably never be invited to that poker game again. You shouldn't gamble anyway, but you get the idea. So quicksort only starts to accrue benefits for you when it's like 40, 50, 60 items or more. And that depends on the compiler, on the operating system, which language you use, how efficient you implement it. And then it kicks in pretty nicely. But for just a few dozen things, don't use quicksort. You're probably better off just using bubble sort. Just need to sort 10 or 20 or 30 things. So this linear median finding algorithm, the threshold is much higher. It probably won't kick in with its benefit until you have to find the median of, say, 1,000 things or 10,000 things even. Then it starts to be a lot better than if you just sorted them and picked the middle element to find the median or something. All right. So with all that, I think we're ready to start talking about computational geometry, which is a very rich area of very interesting problems that occur in many other sub-areas of computer science and are used as subroutines in applications and your GPS system and even your desktop when you move the mouse. There's always computational geometry happening all the time. So we'll talk about convex hulls and Voronoi diagrams. We'll talk about lower bounds for some of these problems, which tend to be n log n in 2 dimensions, the lower bounds. Nearest neighbors, triangulations, collinear subsets, all sorts of interesting things. And it's called computational geometry because the relationships are all kind of geometric in nature. The objects we're dealing with are points, squares, circles, planes, hyperplanes, spheres, cubes, geometric objects, like in a graphics environment, or whenever you have a graphical user interface, for example. So computational geometry is basically algorithmic geometry. Algorithms related to geometric relationships, or from the other direction, you can view it as geometry algorithmicized. Geometry made implementable on a computer, like classical geometry, but now we're running algorithms to determine various relationships. So we'll get a couple of chapters from this book having to do with Voronoi diagrams and convex hulls. How many have seen this book before? It's on the Core Lab website, so if you haven't seen it, it's go there and fetch it. And we're only going to deal with a couple, subsets of a couple of chapters from this. We'll say that I don't expect you to read this whole book. Obviously, there's a lot of stuff in there. And also in the Corman book, there's a whole chapter or two on computational geometry, also convex hulls and range queries and things like that. So look at the Corman book, somewhere in the later chapters. I'm not sure which chapter number it is, but it's towards the end of the book, like the last quarter of the book somewhere. But you already have enough background to read that. It's not like you gotta read these kind of books in sequence in order. It's, algorithms are algorithms. So computational geometry was founded by Michael Ian Shannis in the mid-70s. And with his PhD thesis, he single-handedly invented this whole field, basically, amazingly enough. It's very rare when that happens. When your PhD thesis creates a whole new sub-area of computer science, that's a good day. Actually, that's a good decade. So he did that, and now there's multiple conferences on it, dozens of different conferences and journals and proceedings dedicated to this topic, and probably tens of thousands of papers by now, maybe hundreds of thousands. So it's very fundamental in a number of areas, including graphics, computer gaming, computer-aided design of anything, circuits or blueprints or construction projects, motion planning in GPS systems or GIS, geographical information systems, like the kind of thing that you run Google Maps on and it navigates through the city for you. Computational geometry happens under the hood there in every instance, all the time, every time you use these kind of applications. Let me give you an example of some interesting problems with computational geometry. We'll start slow and then we'll pick up speed and get more sophisticated. So you have endpoints, and you think about a point as a vector, right? They're interchangeable. And you allow some pre-processing, but the objective is once you have a bunch of points that are fixed, they don't move and they don't change, you want to know how many points lie within a certain query rectangle. So I give you a rectangle, and when I give you a rectangle in green there, I ask you how many points are inside. And in this case, there's 5 points inside, but how do you know that? Algorithmically and efficiently, how do you compute that for every possible query rectangle that I give you? So the pre-processing is kind of the initial constant overhead that you do before you start accepting queries. And the idea is that you only have to pre-process once, but you will get a lot of queries. And so the pre-processing doesn't have to be so efficient, but the queries are supposed to be very efficient. Just like Google. Right? Google creates this big database, and kind of now it's fixed, and now everybody makes queries against it, and the queries better be fast. It doesn't matter if Google took like 6 months to index and pre-process the entire database. Queries should be fast. Of course, with the Google database, it also changes over time. Every day there's new URLs. In fact, every second new URLs are added. But here, for now, we'll assume that the points are fixed. So you can just pre-process them to your heart's content. So this triangle or this rectangle has only 1 point in it, this one has 0, and arbitrary rectangles. So how can you quickly determine the number of points in arbitrary rectangles? Let's assume you don't have to report the actual set of points in these rectangles. All you're asked to do is just give the count of how many there are. So it's a counting query, not a listing out query of every object inside. That's a little harder. In fact, that could get out of hand real quick if there's a lot of points in the rectangle. The output size of the list of these points could already be large, and then the query won't be very fast because just listing it would be slow. Never mind finding out which ones are there to list. Okay, so the pre-processing phase only happens once. You can take your time about it. I mean, you don't want to take more time than you have to, but that time could be a lot longer than the query. The query time is critical. Okay, and of course, it generalizes to higher dimensions. So here we see a 2-dimensional instance, but you can imagine what a 3-dimensional instance looks like. I took the liberty of animating it here. So the 2D became a 3D. You'll see it again in instant replay. I'm pretty proud of this one. So 2D here, but when you add 3D axes and shadows, it becomes a 3D problem. Same problem as before. Like you give a rectangular shaped region, in this case a box, and you ask how many points fall inside that box. And you want to be able to do that quickly after you pre-process. So again, applications in databases. So for example, if I ask you how many employees of UVA are between 25 and 35 years of age, and make between, or were born between, I don't know, 1980 and the year 2000. So that's a two-dimensional range query. How do you get that? Because you can sort everything by, on one axis by the year of birth, and the other axis, by whatever else you want. And when you do a double query like that, you're asking how many people fall inside that box along these two axes. It's exactly this problem. So it comes up in databases and geographical GPS systems. So, for example, say you're in Manhattan and you want to know how many restaurants there are, or how many even Asian restaurants, say, there are in this box within 5 blocks up and 2 blocks over. And this query is exactly, again, the kind of query you need to make and be able to answer quickly when you make such inquiries, whether it's Google Maps or Apple smartphone maps or whatever it is. In gaming, it happens all the time. You're in a large space and you want to know how many players are near you so that the game can interact with you with those players, because it doesn't care so much about players that are far away and that kind of thing. So computer-aided design, all these kind of applications require this kind of range query capability. So one common trick to solve problems, if you can't solve the general case or the case that you're presented, you try to solve a simpler problem. And by simpler, you can either make some special assumption about the type of data, specialized data, or often you reduce the dimensionality of the problem. So if you can't solve the 2D problem, try to solve the 1D problem and see how you do there. And then try to generalize the solution from 1D to 2D, and then from 2D to 3D. But one thing is for sure, if you can't solve the 1D problem, you probably have no chance of solving the 2D problem, and certainly not the 3D problem. Why? Because 1D is a special case of 2D when the other dimension is just y is equal to 0, and the x can vary. Okay? So higher dimensional versions subsume the lower dimensional versions almost always. Very few exceptions. So if you can't solve this easily in 2D for fast queries, okay, let's do the 1D. Right? And that's a general problem-solving rule, and Polya, How to Solve It, that book I asked you to read, tells you exactly what I just said, and many other good, clever heuristics, effective methodologies for solving problems very systematically. Okay? So one meta rule here is reducing the dimensionality of the problem. And there's a bunch of others. How many have started reading or have read Polya's How to Solve It, that book? Good, very proud of you. If you haven't, not sure what you're waiting for. You're just depriving yourself of very nice knowledge that will help you a lot in life and in your career. So, okay, so for 1D, you can pre-process the data by sorting it. And once you sort the data, the query rectangle is just a box, it's a subarray of the entire sorted list of numbers. And you want to know how many numbers fall within a certain range. So I'm just showing you the indices here. These are not the values, these are the indices of the array, 1 through n. And these are arbitrary real numbers, or integers, if you don't like real numbers. In the computer, really, there are no real numbers, so you can use a discrete anyway. But I asked you how many of these numbers fall between 27 and 53. Well, once the numbers are sorted, you can easily find out how many. How would you do it? We have a bunch of numbers, we just sorted them. And I asked you how many are between 27 and 53. Thank you. So how would you do it if the numbers are sorted? Not a trick question, but silence won't solve it. Yeah? What do you say?
Search for the two numbers.
Binary search?
Binary search, yeah. So we basically do a binary search on the values of the lower end of the query, in this case 27, then you do binary search on, what would you say, 53, and see which numbers in the array are closest to those two, and then you know their indices, I and j, and so what's the answer of the count? J minus I plus 1, and that's the answer. So that's the 1D version. So it's log time per query, binary search. right? And then the space you took to do all that is basically linear. You took the data and sorted it into a secondary array, or you can even sort it in place if you're allowed to modify the data, that's okay. Either way, it's just linear space. And then n log n pre-processing time, because that's the time to sort. Right? And how do you sort? Well, merge sort, or anything that works in n log n time. Heap sort, whatever you'd like, as long as it's n log n. Okay, any questions about the 1D version of range queries? Because the 2D will be more subtle, more complicated. Not too bad, but it's not as simple as a binary search. Okay. It's also not as simple as sorting, because sorting is a one-dimensional problem. The dimensionality of sorting is kind of hardwired into the very nature of the problem. You're just sorting one variable. Right? There's a total order, and total order implies kind of a one-dimensionality to it. Everything is in a row, like ducks in a row. Everything is bigger than everything that preceded it. But for 2D, there's not even a definition, a good definition of what it means for two-dimensional point set to be sorted, or three-dimensional, or any higher dimensional. So sorting by itself is not even well defined for multivariable data, multidimensional data. Never mind how to accomplish such a thing, even if it was defined exactly. So there's no total order. There's partial orders. But, okay, but the same problem, you have a query rectangle and you want to know how many points on its side. So we're trying to find out how many points are inside the green triangle. But in general, there's a lot of them, and it's tricky business. But let's say we knew how many points there are inside this purple rectangle, and separately we knew how many points inside the blue rectangle, and we also knew how many points are inside the yellow rectangle, and finally how many points inside this red rectangle. So there's 4 rectangles induced by this original green rectangle. How many can see that? They're completely well defined by the original green rectangle. Right, so again, instant replay, the green rectangle sort of defines the purple one. That's just the green boundaries, but extended all the way to the origin, stretched out to the origin. The lower left point of the green is stretched out to the origin, and you get the purple one. The blue one is the one at the origin that only touches the green on the left. The yellow one touches it on the bottom, right? And the red is from the origin to the lower left of the green. So any rectangle that floats around the plane immediately induces these 4 other rectangles uniquely and in a well-defined manner. So let's say you were trying to find out the green, and you don't know the green, but you knew the purple. And let's say you also knew the yellow, which is this one, kind of putting it in context for you. And then you also knew the blue count, how many points are inside the blue. And you knew how many points are inside the red. What's the relationship between the number of points in green and the number of points in these other 4 rectangles? It's not hard. How would you compute the first from the next 4? Yeah, so this would be minus that and minus that, but because you subtracted the lower portion in red twice, you got to add it back in once to get the correct count. Okay, so minus minus plus, and this is called the inclusion-exclusion principle, and for good reason. Once you exclude a couple of things, you got to re-include some things that were excluded more than once, and you got to account for that. And once you do it properly, you get the right count, and it's only 4 of them, and those are easy to compute in the original green because you'll see in a minute that there's not too many possibilities for these 4 where they can lie. And anything else other than those 4 will be the same answer as one of those 4. And we'll see that in a minute. Okay? So for example, if there's 9 in the purple and 4 in the yellow and 3 in the blue and 1 in the red, 9 minus 4 minus 3 plus 1 is 3, and that 3 is the correct count for the green rectangle. So it all works out. And more generally, when you have 2 sets A and B, and you have the intersection A intersect B, and these are arbitrary sets, but if you take the counts of A and B, and also the count of A intersect B as a subset, the number of elements in A union B is the number of elements in A plus the number of elements in B minus the intersection. Because when you add A and B together, you're adding the intersection twice, so you gotta subtract it once to get the right count. Okay, so that's inclusion, exclusion principle. And it's not just about boxes or points in the plane, it's a general principle about sets of anything. And by the way, this generalizes to more than 2 sets. Now you can see how it would generalize to 3 sets. What do you think it would look like in 3 sets? A, B, and C. So the cardinality, number of elements in A union B union C is what? The cardinality of A plus the cardinality of B plus the cardinality of C, then what? Minus all 3 intersections, plus, and so you got a minus and plus, and if there's more sets, you got a minus and plus and minus and plus, all the right portions that get subtracted more than once and then added, and if you added more than once, you gotta subtract it again, and it gets a bit tricky, but it's a relatively fixed, predictable pattern as you take more and more sets. So this is a very general principle, not just for 2, but for larger numbers of sets. Okay. It's called inclusion exclusion in general. Kolya talks about it in his book, and it talks about a great many other things too. All right, so with that knowledge, we're going to compute the number of elements in every possible rectangle that's starting at the origin. It has the lower left-hand corner in the origin and the upper right-hand corner somewhere else. And those are much easier to deal with an arbitrary rectangle because they're more structured. It only has one corner in the origin. So let's say the number of points in this one is 6. But if you slightly extend it out, if you stretch out that rectangle to this slightly larger rectangle, and it doesn't touch any other points while you're stretching it, the number of points inside will remain a constant 6. How many can see that? It's not touching any other points. The only time when the count will change is that as you sweep it out to a larger size, stretch it, it'll touch or cross another point, either to the left, or either to the right, or upwards. And this triangle, this rectangle also in green, slightly larger than the other rectangle, will also have 6. And counts will only change if you hit another point. And so these critical lines past which, if you stretch out a rectangle with the lower left corner in the origin, there's only a discrete number of vertical and horizontal lines past which, if you sweep past them, the counts will change. But if you don't sweep past one of those lines, vertical or horizontal, the counts will not change. How many get that? Okay, pretty straightforward. It's not an algorithm yet, but it's an important insight, which will give us an algorithm. So if you want to know the count over here, you can do exclusion inclusion on all the other rectangles that are associated with this one, and the counts for all these other rectangles, you can pre-compute them, and you can pre-compute them reasonably straightforwardly. Okay, so these regions are defined by horizontal and vertical lines passing through each and every point of the set. These are the critical lines. If you're stretching something within such a region, but not crossing one of those blue boundaries, you're not changing the count of whatever rectangle is getting stretched to that region. So all you gotta do is compute how many points there are in every rectangle that lays on these blue lines as boundaries, as the rectangle's boundaries lie on these blue lines, whose left bottommost corner touches the origin. And once you do that, you can do inclusion exclusion. We'll do a little bit of binary search. So let's see how that works. And let's say you want to find out the number of points in this green rectangle. So first we pre-compute the number of points in every rectangle that it's rooted at the origin that hits those blue lines, either horizontally or vertically. So the counts are all zeros here, okay? But the count here for this rectangle here is 1 because you just swept past this first point. And the count is 1, 1, 1, 1, 1. And the count is the count from the lower row plus as you sweep to the right, any new points that you sweep past. Okay, so the count is still 1 and 1 here because these are ones, but now you're going to sweep past these 2 points, and the count here will become 2. Okay, and it'll be 2, and then as you sweep past more points, the counts keep increasing. So, as a sweeping line algorithm, as a kind of a sweep of this two-dimensional matrix of values, keep clicking up as you hit more and more points, and as you do, those counts keep increasing. And again, those counts over-represent the number of points in a rectangle whose upper right corner lies anywhere in this region, and its lower left corner is always the origin. So here we passed another couple of points, so the count now is 4 for any triangle whose upper right-hand corner is here, and so on and so on. And you just keep doing that. Now, how many of these counts will there be in total? How big is this data array that keeps track of all these counts in terms of the number of points? Number of points is n, there's n points. How big is this array of counts in terms of n, number of points? Not a trick question. N squared, yeah, n squared. N squared is not great, but it's a heck of a lot better than n cubed or n factorial or some exponentially n or a much larger n. And remember, that's a pre-processing step. You only have to do that once. And then you can do trillions of queries and never pre-process again, assuming the data set is fixed. Okay. So when you have a query rectangle like the purple one, you take the count of that and then you subtract the 2 counts by inclusion exclusion of the other 2, and then you re-add the count of the lower one, and when you do all that, you get the right answer. Okay. So for example, the green rectangle, its upper right falls into the 6 category. So that's 6 points of any rectangle that falls here that's rooted at the origin. But this rectangle here is not rooted at the origin. But the other rectangles that you're going to be dealing with are. So the 6 is, and then the 1 will be here, the 4 will be here, then the 1 in red will be here. Everything is color-coded to match. And then the answer will be 2. And sure enough, there's 2 points here inside the green rectangle. Yeah, derived by inclusion-exclusion, just like we saw in the previous slide. Now, the big question here is, how long does this take per query? Okay. So once you do all this, remember these lines, the blue lines, are defined by the point set. Let me just clear out the rest of the text. So these blue lines are defined by the red points. It's basically horizontal lines through all the red points, and then vertical lines through all the red points. And then you basically, the array is sorted by these values. So in each entry of the array, you have the value of the point that induced that line, the x coordinate of that point, and also the y coordinate of that point. But it's sorted by x's, and then separately it's sorted by y. The rows are sorted by y, the columns are sorted by x. And what are these x's and y's? Well, these are the coordinates of the original red points that induced all these blue lines. So now the array is nicely sorted independently by the x's and independently by the y's in terms of rows and columns respectively. And now you can do a binary search to figure out where in this array the corners of the green query rectangle falls into. And you can do that with a binary search in the x, and separately a binary search in the y in this big matrix. First you search the columns, then that will give you the x. Then you search the rows, that will give you the y, and then you'll know which little sub-rectangle that corner falls into. And then you do it for all the other 4 corners. Then you do mutual exclusion, inclusion to do minus, minus, plus, like we saw in the previous slide. Do that arithmetic and you get your answer. And all this is happening now in logarithmic time because the bottleneck here is the binary search. The arithmetic doesn't take hardly any time at all, it's constant overhead. And you already said that the space is quadratic, And also the amount of pre-processing is quadratic also, because you don't have to recompute everything from scratch, you just compute these values, you just kind of scan left to right every row by increasing rows, and the counters click up, and you kind of save all these values in this two-dimensional n by n array, and it's quadratic space and quadratic time. And the query time is logarithmic. How many understand all this? That was only a quarter of the class, so you want to ask questions, or any questions or issues? Or, yeah.
Can you repeat how we count when we were sweeping past?
Yeah, so the counts, so you start at the origin and you sweep to the right. And as you sweep to the right, so you ask yourself internally in this rectangle that's upper right hand corner is this point here, or this point here, or this point here. How many points are there are internally? Strictly in the interior, not on the boundary of these rectangles. So the answer is still 0 here and 0 here. Let me try to draw something. So for this, the answer is 0. And then for this, it's still 0. And for this, it's still 0. And you keep going. And then it's 0, 0. So where do you get these 0 on the second row? Well, you get them from the first row. So starting here, this first value you start with is whatever that value right below you was. So you start with a 0. And then you keep going until you sweep a point. Okay. And when you sweep a point, that's still 0, but now it's 1 because this point here was swept. And that's internal to this rectangle. Not sure how to switch colors on this thing, but and then you keep going, and as you keep going, you keep clicking up this counter. And how do you know you just swept a point, by the way? That's not a trivial question. Yeah.
The upper right x and y boundaries are, those values are greater than the xy coordinates for the point of what you just.
Yeah, the xy of this the xy value of the upper right hand corner of this kind of expanding rectangle exceed that of that point. But how do you know that it does? You have n points, so how do you make that check? And you're going to go after each and every point to compare for every time you expand, then it'll be n cubed, right?
Do you know the coordinates of the points before you start?
Yeah, the points are given to you; they're fixed as part of the input.
Could you just find all points between two values of x, or so if maybe this isn't answering the question, but I would just for the box I would look for all points with, say for x, x values between, say, a lower bound and an upper bound, and
Sure,
y values.
but now you're talking about a binary search, and only after you sort the x coordinates of the point. So it'll give you an n squared log n pre-processing. Right? How many see where this discussion is going? Okay. So what do you do? Yeah, so what you can do is you can sort all the points by x coordinate before you even start. How expensive is that? N log n. So compared to the n squared pre-processing time that we're going to spend, n log n is a freebie. So just do it, take it, sort them. Whenever you can sort something for free, yeah, chances are you should probably do it. Your life will be easier when you have to interact with that set if it's sorted. Not always, but that should be kind of your knee-jerk reaction. Oh, I got n log n or more time? Well, okay, sort for free. And then move on and things will be easier. Okay, so sort all the points by x coordinate, and you have a sorted list by x. So as you sweep that line, you keep going up that list of x coordinates. And when you reach a point where the thing expanded, you know you just hit something, because you check the y coordinates of everything that's up to that in the x coordinate. And if the y is within that box, you know you just swept the point and you need to click it up. Okay? And you just keep going. So moving down a sorted list from one end to the other and sweeping it once is just linear time. But to process a whole row is linear time anyway. So you're not being inefficient, you're just being exhausted. And it works, and you're not losing any more time than the allotted time you have for pre-processing anyway, which is n squared in this case. Because even the array size of n squared, just initializing it takes n squared time. So you might as well give yourself this leeway with n squared time and do it systematically by kind of sweeping up in the x coordinates, and eventually you'll see you swept something, and then when you start the second row, you take that list from scratch again and start scanning it from the beginning towards the end again, and again, and again, once per row, and that list is n long. Okay. So basically, that will get you the pre-processing in quadratic time. You know, maybe think about it kind of offline a little bit, convince yourself that it works. Read the description of this in the Shamus book, which I think is chapter 2 probably, and that'll give you a reinforcing kind of exposition of this, and without the beautiful graphics, but in other words, in different kind of language, and maybe that will shed some more light in your mind on how these things interact. Yeah.
Are we counting lines or counting dots on the green line inside the box?
Let's just say the count is internal to the box, not on the boundary. So, if you want on the boundary, you can always increase the box size by epsilon in every direction, and then all the boundary points will become internal. You can always pull that trick, increase the size by epsilon in every direction. Yeah.
All the horizontal and vertical lines, they pass through a point, right? The blue lines.
Yeah.
So, but there is a line that do not pass through any point. So, why is that even the second vertical line from the left?
This one here?
No, from the left.
Oh, from the left. This one here?
Yeah.
Oh, we passed this. I thought there was a point. Let's see. Did I have an extra line here? Oh, okay. Maybe it's an extra line. Oh, I think you just discovered a typo. There's no point that corresponds to that. So this second vertical line from the left shouldn't be there. Extra credit right there. You got me. I was wrong. Some of our politicians should admit when they're wrong, but you know, that's asking for a lot. But anyway, I was wrong. I'll give you extra credit. Thank you. Great. Now that you mention it, does this hurt that there's this extra line there? Not really. But if there's too many extra lines, it can start increasing the complexity unnecessarily. So, in terms of the time complexity, it doesn't change the correctness of the method. But you're right; it might as well not be there, and you won't be worse off for that. Okay, excellent. I'm glad you're thinking about it. So that's good. What else? Any other questions? So this works pretty nicely. Soon we'll see how to do more general range queries and point location queries, and things will get more esoteric than this. But here, it's pretty well behaved. Mostly because these are rectangles. And not just rectangles, rectilinear rectangles with sides parallel to the axes. If the rectangles were skewed, all bets are off. You have to start worrying about what happens then. But for now, it works pretty nicely. So logarithmic time per query, it's about as good as it gets. You can't do general queries in better than log time, almost ever, unless it's a very specialized kind of situation. Information theoretically, log time is kind of the minimum entropy. Log is sort of minimum entropy necessary to distinguish n things. If you think about the information theoretic terms, but if you don't know what I just said, don't worry about it. Just read a little bit about information theory and you'll see what I'm saying. Now, the space and the pre-processing are both quadratic. It turns out that with a lot more effort, you can do better than that. So, by the way, the naive method, if I give you a query rectangle and there's no pre-processing allowed, and I ask you how many points of this set are inside, there's no easier way to do it other than look at each and every point, and for each and every point, test whether it's inside or outside that rectangle. That's a constant time check. But after linear time, you'll know which ones are in, which ones are out of that query rectangle. And so you're not using any pre-processing time, you're not using any space to pre-process anything, but the queries are long, they're linear time, not logarithmic. And by the way, the relationship between logarithmic and linear is an exponential relationship. How do you understand that? 2 to the log n is n, by definition of the log. Right? So don't underestimate how quick the log is, or how slow linear is compared to the log. They're exponentially far apart. So it's not just a little bit of savings, it's a huge saving. So the clever method we saw in the previous slide, the pre-processing time and the space rose from constant to quadratic, but the query time dropped from linear to log, and that's an exponential improvement. And that's really good, especially if the input doesn't change much and you have a lot of queries coming down, like Google does, or almost any website or application. Now, it turns out you can do something in the middle, a trade-off, where using KD trees, you can have the pre-processing and the space both drop to n log n, so that's a lot of savings in space and pre-processing time, but the query increases to log squared. It's no longer log, it's the square of the log. Now, square of the log is not too bad either compared to linear, but it's not as good as the log, it's the quadratic of the log. So you pay a little bit. And KD trees, we're not going to harp too much on them now, but it's basically a way to subdivide a space into regions based on where objects in the regions lie, like points or other objects, in a kind of horizontal, vertical, alternating manner, so that you can kind of recurse on the space, left, right, horizontal, vertical, alternating, and converge on what you want pretty quickly. It's a kind of ubiquitous data structure, and it can work in higher dimensions too. Here's a KD tree in 3D. And by the way, the algorithm we saw earlier works in 3D also. So this algorithm that we saw on the previous slide, that can be easily generalized to 3D, using a 3D array and 3 binary searches, one on the X, one on the Y, one on the Z. And that, how many can see that generalization? You can sort of imagine how that would work, pretty much on the same principle. Exclusion, inclusion would be a little trickier, there'll be more sets to include and exclude. The time to pre-process and the space to pre-process would be what in 3D? And Q, now you get it. And you can generalize it to dimension 7 or dimension 23. Now it's going to, the time and the space will start to run away from you if you get into higher dimensions. Even 3 is kind of onerous. But if you go to KD trees, it's not so bad. You get square of the log and n log n space in 2D and 3D will be a little bit more than that, but not hugely more. Now, there's all sorts of generalizations you can do on this kind of problem and solution. You can already, we mentioned you can already do it in higher dimensions. And the general search window, it doesn't have to be rectangular, and even if it's rectangular, it doesn't have to be parallel to the axis, its sides. It could be arbitrarily angled rectangle, then it gets more tricky. It could be a circle with a range query window. It could be a triangle, it could be arbitrary shapes. Right? So the queries can come in arbitrary polygonal shapes, and that makes it much harder. Or it could be half-plane queries. You give me a half-plane, you ask me how many points fall on one side of the half-plane versus the other side of the half, let's say the lower half, or the right half of the half-plane. Or they can be arbitrary objects instead of points. So we kind of did this problem with points, but imagine if all the objects were line segments instead of points, or triangles, or star-shaped, or hexagons and pentagons, or a mix of those things. And ask you how many of these objects are inside a query point. Now it gets a lot more complicated. We also did a counting kind of version of the problem, not an enumeration version. So far we answered how many points are in this query rectangle, but not which ones are they exactly. And so reporting the whole roster is at least as hard as counting, and often much harder, and the query time can no longer be just log, because the count could be much higher than the log, and listing it out will take at least as much time as their cardinality. So if there's a lot of points you need to report, it'll take it that much longer to report them, and so the query time, including the reporting time, will not necessarily be bound by the log anymore. If you're lucky, it'll just be the number of points. If you're not so lucky, it could be higher than that. So there's lots of ways to generalize this, and people have done many of those things. And we also talk about containment versus intersection. Points, it's either in or out, but if you have a segment, the segment could be in, or partially in or out, or completely out. And similarly for other more complex objects and graphics applications and video games and CAD systems, you may want to solve a lot of these kind of sub-problems separately and efficiently. You could also solve the static versus dynamic version. So right now we solve the static version. The point set doesn't change. It's fixed. It's given to you. And once it's given to you, you're stuck with it, and you don't have to worry about it changing at all. So you can pre-process and then do arbitrary numbers of queries, but the point set is fixed. You can do a dynamic version where points keep getting added over time or subtracted. And now you always have to answer queries correctly, but you also have to update underlying data structures and keep doing pre-processing as you go, so that you can keep answering queries quickly, but it's a dynamic version of the data set. Points are added and subtracted. And a lot of real-life applications, that's exactly what happens. Certainly to the Google database of URLs, URLs get added and subtracted on a second-by-second basis, probably a millisecond-by-millisecond basis. And you constantly have to do good, fast queries as you go. So often you can take a problem and generalize it to a dynamic version, and things get a lot hairier. In most cases, the dynamic version completely subsumes the static version. Okay? Because in the dynamic version, things may change, but they don't have to change. And if they don't change, you got a static version, which solves the original, easier version of the problem. Then there's online and offline versions, and you can get into all sorts of generalizations of this kind of problem. So we just did a basic version where the objects are points, nothing more complicated than that, and the query rectangles, the query regions are rectangles, not anything more esoteric than that. But you can imagine how we would start generalizing in all sorts of dimensions, and you can have combinations of these. You can have a four-dimensional where the objects are arbitrary polygons, or polytopes, I guess, in higher dimension. And then it could be dynamic on top of that, and you want to separate intersections from containments, and on and on and on. You can have a combination of these variations together, and then you get more and more complicated scenarios. So people have looked at hundreds of these kind of types of problems and variations and over the decades, and I just showed you here the most basic version. In the Shamas book there's a little bit more complicated versions, and if you want to see really interesting versions, weird versions, then you can go to the literature of computational geometry and you'll see plenty of that. So speaking of polygons, let's talk about polygons. So a polygon is a closed sequence of vertices like that, where the last connects to the first. And a simple polygon has no self-intersection. These polygons can intersect themselves, and then they're not simple. It has an interior and exterior. It can be convex and non-convex. And the interior-exterior it's kind of intuitively obvious what's in and what's out of a closed simple polygon, non-self-intersecting polygon. But it's actually not a trivial matter. In mathematics, it's something called the Jordan curve theorem. And basically it says a simple polygon partitions the plane into three regions: the interior of the polygon, the exterior of the polygon, and the boundary of the polygon itself. And it's not just about polygons, it's arbitrary closed curves, simple closed curves. They can be parabolas or ellipses or sinusoidal kind of shaped closed curves. And it's actually not easy to prove this. And one of the reasons it's not easy to prove this theorem, simple though it may seem, it could be simpler than, there's an outside, there's an inside, and the actual boundary of the figure. Well, there are manifolds where that's not true, actually. So if the polygon is on a Mobius strip, or on a projective plane, or on a Klein bottle, and these are weirder manifolds, surfaces, than just a sphere or a plane, that theorem is not even true. There's no exterior and interior, necessarily, on a Klein bottle and on a projective plane, and things like Mobius strips and Mobius strips only have one side and one surface. If you don't believe me, construct one from paper and try to paint it on both sides, you'll see that the paints clash. Anyway, if you're not sure what all this means, maybe read about it, don't worry about it too much, but I just want to bring it to your attention. Anyway, convex polygon is a polygon contains all of its pairwise segments made of vertices. So another way to think about it equivalently is it's the intersection of the half planes that the different sides of the polygon define. If you take a half plane, put it on every side of the polygon, take all these half planes together, the intersection of all of it is the polygon itself, it's the interior of the polygon itself. There's a lot of equivalent definitions of convexity. You can also think about it as a linear combination of all of its vertices, any linear combination. Okay? A polytope is just a high-dimensional polygon, like a cube, right? Or one of those other Platonic solids, dodecahedron, dodecahedron, octahedron, or any other more complicated shape. Okay, and conventional geometry deals with all of them. That's one of the Platonic solids right there. There's 5 of them in 2 dimensions. I think in 3 dimensions, I think 4 dimensions is probably 7. Somebody should check me on that. This is a tesseract. This is the shadow of a tesseract rotating in 4D. A tesseract is just a 4-dimensional cube. How many heard of tesseracts or 4-dimensional cube? Okay. If you haven't, don't worry about it, but there's very interesting properties of these objects. And here we see a 2-dimensional shadow of a 3-dimensional, a 2-dimensional projection of a 3-dimensional shadow of a 4-dimensional cube. Your shadow is always one less dimension than yours. So, if you stand in front of a light source, your shadow will be flat on the floor, 2-dimensional, because you're a 3-dimensional. If you have a 4-dimensional object and a light source, your shadow will be 3-dimensional, not 2. So the shadow of a tesseract is 3-dimensional, and this is a 2-dimensional projection onto the screen of a 3-dimensional shadow of a 4-dimensional object. That's one way to visualize it. It looks all kind of squishy, but it's a rigid object. Okay. Anyway, how many read Flatland, the novel Flatland, or heard about Flatland? Okay, if you haven't, it's another thing you may want to look into. It's a beautiful discussion of dimensionality. Couch is kind of almost like a children's book, but it's very subtle and interesting. Okay, but I digress. So point location inside polygons. So you have a polygon, and you want to tell if the point is inside or outside. Now visually it's obvious, but algorithmically it's not so obvious. Because I give you the polygon as a sequence of points around its exterior, around its boundary, and then I give you a query point, and how do you begin to determine whether it's inside or outside that polygon? And you want to do it fast, obviously. You want to do it reasonably quickly. Now, if it's a one-shot problem without pre-processing, there's several things you can do, right? Basically, you cast a ray out, beginning at that point, out to infinity, and then ask yourself, how many times does that intersect the polygon? And if it's inside the polygon, when you cast out that ray, it'll only intersect an odd number of times if it's inside, but an even number of times if it's outside. Potentially 0. And there's a few other exceptions, there's a few kind of boundary cases to that I'm going to point out. But the polygons could be arbitrarily dimensional. It's easier if they're convex. Right? There's certain tricks you can do. Convexity is your friend, basically. If you have a situation where objects are convex, there's things you can leverage, properties you can leverage to your advantage, algorithmically and even mathematically, and that you can't really leverage or benefit from if the objects are not convex. Convexity is your friend, usually. There's lots and lots of applications of this point location queries. Whenever you click the mouse on your screen, the operating system needs to know which window you clicked on. Which window, usually windows are rectangular, but they don't have to be. Operating systems can have arbitrarily shaped windows. How many knew that? Usually they're nice and rectangular because that's the typical case. But windows can be elliptical or they can be arbitrarily polygonal. And when you click on something, then the system needs to know which window you clicked on. It's not a trivial operation. That by itself is computational geometry happening right there under the hood whenever you click on your screen, whether you realize it or not. In GPS systems, we already said it, it happens all the time. You wanna know where you are, and the boundaries of the states of the United States, you can model them as polygons, complicated big polygons, and just knowing which state you're in is one of those queries again. Which polygon are you in? Are you inside Virginia or outside Virginia? Never mind exactly where outside, but these are all point location problems. In motion planning, in computer-aided design, in graphics, in gaming, there's lots and lots of these point location problems that you need to solve. And so the question is, how do you do it efficiently? So by the Jordan curve theorem, there's interior, exterior to every polygon, every simple closed curve, in fact. So you can raycast. Basically, you start at the point that you're given, and you shoot a ray out to infinity and ask yourself, how many times does it intersect the blue polygon? And if you're inside, it'll intersect it once if it's convex, or 0 times if you're outside, or twice if you're outside, shooting towards the polygon itself. It'll intersect it twice before going off to infinity. So 0 and 2 means you're outside. It's only once means you're inside. And there's a couple special cases I'll bring to your attention in a minute. It's not quite that simple, but that's the general idea in most of the cases. How do you get that? Okay, so it's an even odd kind of situation, argument. If it's non-convex, kind of the same thing. If you're inside and you're casting to infinity, you'll intersect it once, or maybe 3 times, or maybe 7 times. But if you intersect it that even number of times, you're on the outside of it. Again, there's a couple of special cases I'll show you later. And how do you test the intersection between a ray and a polygon segment? Or more generally, how do you test whether 2 segments are intersecting or not intersecting? I'll give you 2 arbitrary segments oriented arbitrarily. Each segment is defined by its 2 endpoints, uniquely defines a segment. 2 endpoints uniquely define a segment. I give you 2 segments, ask you, do they intersect or do they not intersect? Algorithmically, let me ask you this first, it's probably the easier question. How fast can you do it algorithmically, determine this intersection or non-intersection for 2 segments? Take a wild guess. How fast? It's not a trick question. Think about it, it's kind of obvious. Right? Is it n, log n squared? It's kind of all of the above, because n is equal to what? 2. So, how do you do it? How do you test for intersection?
Zoom of multiplies on both the lines of those kind of.
Yeah, you basically, it's basically a few nested ifs, if you will, right? 2 things intersect, right? If the x of 1 falls between the 2 x's of the endpoints of the other segment, or vice versa, and you can put a couple other conditionals and see that with a few if statement, kind of nested if statement, you can determine in constant time whether 2 segments intersect. How many kind of believe that without necessarily going through all the if and then else's? Okay. As an exercise, go through it, implement it, make sure it works. At least once in your life, just implement pair of segment intersection test. Again, there's not even a loop, there's nothing to loop on, it's just 4 points and 2 segments, defined by the 4 points. So you can test intersection of this ray against any of the segments, and then count how many there are, and then you'll know if it's inside or outside. Again, no pre-processing because it's a one-shot problem. In a minute, we'll see what happens if you need to solve it over and over again. You can save a lot of time in the query. But it's linear time, because you intersect that ray with each and every blue segment of the boundary of the polygon, and then you count how many intersections there are, and then you'll know by the even oddness of the number of intersections whether you're inside and outside, respectively. So odd means interior, even means exterior. So like 4 times, that means you're outside. Once, you're going from the inside to the outside. That's a nice little property of simple closed curves. Now here comes the few minor exceptions. So here I'm saying that segment intersection segment pair intersection, that is a constant time, and you can do the ifs, if then else's and so. Let's say you intersected this way. So technically, it's a tangent, it's not quite an intersection of the interior of a segment of the boundary. You're intersecting two segments, both on their endpoints. Two segments of the boundary on their endpoints. So it's a bit misleading here because the number of intersections here, it's still two. Because you intersect this segment here on its end and this segment here on its end. So really you were still outside. And so that's okay, but it's kind of a little oddball case. These two intersections are not quite like these, because these intersect on the interior of boundary segments, and this other case intersects at the very tip of the segments. Here's another weird case. If you're inside and intersect, again, the corner here, you have to distinguish this from this, because here you also intersect both of these segments on its tip, and there's two intersections. But remember, even means exterior, but this is interior because you went right through the corner. So that's a weird special case, doesn't happen very often, but you need to worry about that. And you need a couple more ifs in your inner logic of your loop or whatever, but you can get around that and handle it. And there's a couple other cases. What if you're on the boundary going out and you're going parallel to the boundary on the boundary itself, and you're intersecting a whole bunch of points on the segment, but really, as far as endpoints go, you're intersecting two, but now you're on the boundary. It's another kind of weird boundary case. Literally a boundary case, but no kidding. Boundary case for real. It's on the boundary. Now you know why they're calling boundary cases, right? So, well, here there's an issue of definition. If you're on the boundary, do you want to be inside or outside? Considered to be inside or outside if you're on the boundary. That's a matter of definition. But anyway, once you kind of have a little bit of logic with some if statements to take care of these weird cases, everything works the way we described earlier. And I just want to bring it to your attention that you have to kind of worry about these. You have to worry about these boundary cases, literally. And in general, in programming and in logic and in math, you have to worry about a few special cases, a few exceptions potentially, whenever you solve a problem. Don't just say, oh, okay, it's general enough, walk away, raise your hands in victory, and say, oh, by the way, you missed this, I missed that, and there's a couple of if-then-else's that I didn't consider, and the solution is not quite general or not quite complete, but it's 99% correct. Usually, if you're 99% correct, nailing down the last few kind of problematic corner cases is not too hard, not too bad, usually. But you have to be aware that this is a thing. This happens quite a bit in real life. Anyway, constant space, constant pre-processing time, but linear amount of time per query because you're only doing it once. And what's the lower bound for this problem? Can you do it in less than linear, you think, if you just do it once? The query time? How many say less than linear, sublinear is possible? How many think that? They say linear is a lower bound also. Well, nobody's voting. Not a single person voted. That's a perfect record. Okay, maybe I should ask the question again. Maybe we can get the question. So we just showed the linear time algorithm for querying, answering the question of whether a point is inside or outside a polygon. And then I said, well, is linear also a lower bound? In other words, is this an optimal algorithm? Or can you do it faster than linear time for a one-shot problem? No pre-processing. I would say linear is a lower bound. N is number of points, vertices of the polygon. Is N. The number of vertices is N. What do you think? By now we've kind of seen a lot of, well, not a lot, but a bunch of lower bounds. Right? So intuitively, I'm not asking for a proof right this second, but intuitively, do you think N is a lower bound on the one-shot problem? When you say, yeah, N is a lower bound. Yeah. We're getting there now. Now you're getting it. N is a lower bound. Why? Intuitively, why? Not necessarily a mathematically rigorous proof, but intuitively, why is N a lower bound? Yeah.
You're gonna look at every point.
You got to look at every point, because if you don't look at some point, what could happen?
You don't know if it's out there or
Yeah. You don't know if that point is like 2 miles down the road or right there next to the point of the query, and both situations will completely change the answer, right? If the query is here, and this point here would be stretched all the way down here, this point will fall inside instead of outside. But if you answer the question without looking at that point that could have been stretched somewhere, that completely would change the sense of the answer, you can't possibly be always right. Because you don't know which way it would have gone in general. How do you understand this? This is called an adversarial argument or an oracle argument, a bad oracle argument. The argument is not bad, the oracle is bad. Because he's trying to defeat your correctness by doing arbitrary things behind your back, and if you thought you were right, he would go ahead and change it in a way that you wouldn't be right. So, and that can easily be done by moving a single point over. And so if you haven't looked at that point, you don't know where it is, so you don't know what's the answer. So you can't possibly be correct in general, and that's the adversarial argument that says every single piece of the data of the input must be looked at least once. That's a lower bound, no matter which algorithm is running. So it's general lower bound. Okay, here comes the interesting part. Well, everything was interesting still, but this is even more interesting. So now, I want to pre-process the polygon in a way that will make queries fast. So I'm going to take my time pre-processing. You have lots of time to pre-process, but the queries are going to come fast and furious after the pre-processing, and you better handle them quickly and not take linear time. That's too long, right? So here's how you can pull off that stunt. You can pick a point inside the polygon and partition it into triangles like a pizza pie, right? So these are the slices, and so you pick an interior point, any interior point will do, and you can partition it into triangles like that, any convex polygon. And then later we'll see how you do this for a non-convex polygon. It's more complicated, but it's still doable. For a convex polygon, you can always partition it into triangles. How do you believe that? Yeah, take any point in the middle and just shoot rays from that point to all the vertices, and you got your slices of pizza. And there's no two ways about it, right? How do you find an interior point, by the way? It's not hard, but how do you do it algorithmically? By the way, which interior point do we want? If we just want to slice it into triangles and without any other constraints or goals. Any interior point will do this trick. Right? How do you find any interior point, no matter what it is? Just not a trick question, but you gotta do something algorithmically. You can't just say it'll happen by itself. I give you a polygon. I ask you to find a point that lies inside the polygon. There's n sides to the polygon. There's n points around the periphery. Yeah. Yeah, take the average of the x's and the average of the y's. That'll be guaranteed to be in the interior. How do you believe that? Yeah. There's another name for that point. What is it called? Center of mass or centroid. Yeah. Good. All right. Sort the pizza slices by the polar angle around this interior point. You can start anywhere you want. So that's slice number 1, 2, 3, 4, 5, 6, and 7. All right. So you sort these triangles by polar order, by polar angle order around this interior point. Which point? The centroid, or any other point that's inside. Okay. Now here comes the query. The query says, is this point inside the polygon or outside the polygon? Remember before, it took us linear time to figure this out. Now, we can do it much faster. How? Compute the angle of that point to the centroid, whatever the interior point is. Compute the angle of this to P. You can do this in constant time. I draw the line, take the sine, cosine, whatever, you can compute that angle quite easily. How many can see that? Never mind exactly, just trigonometry, just use trig. Okay, I'll leave it at that. All the other slices have their own angles. Right? And we sorted everything by the angles of the slices. So to find whether this point, which wedge it's in, not necessarily which triangle it's in, but which wedge. The wedges start with the triangles, but they go off to infinity. So it's like infinite pizza slices in all directions. where the triangles are just the base of the slice. So to find what wedge it's in, how fast? Log n. By what technique? Binary search. Yes, my Padawans, I'm so proud of you. Now you're getting it. So in binary search manner, you find what wedge it's in. Logarithmic time. And there could be lots of wedges, there could be millions of wedges. But in log n time, you will find which wedge it's in. And once you find it's in this wedge, you gotta do one more test. Now you know it's in this green infinite wedge simply by the virtue of its angle being within the two angles of this wedge. The wedges are all sorted by their angles. Right. So what's the next test you gotta do? Find out if it's inside this triangle or outside that triangle. They'll tell you if it's inside the polygon or outside that polygon. How quickly can you do this test? I give you a point in a triangle and ask you, is it inside or outside that triangle? How fast can you do that? Constant time. How? I'll leave that up to you. It's just a few if statements. It's like 9-segment intersection. It's just a little bit different. One easy way to do it, take all three sides of the triangle, consider them as half planes. So you have this half plane, and then this half plane, and the triangle is the intersection of all three half planes. How many can see that? So just make sure that point is on the correct side of each of the three half planes, and if it is, it's inside the triangle defined by the three half planes. How many get that? That's an easy way to test. There's other ways to test as well. So, what does this give us? With some pre-processing, you can tell if a point is inside or outside a given convex polygon in logarithmic time per query, and it's based on binary search. And it presumes within the pre-processing of sorting everything by the polar angle. And how long does it take to do the pre-processing? And log n. By what method? Sorting. Good. See? Now you're using all the other algorithms we went on for the first few weeks of the course. Now you're using them as subroutines. Sorting and pre-processing and all that stuff are being very handily used as subroutines in solving larger and larger problems. The space is linear because you got to store all these wedges or triangles, if you will. But in n-log n pre-processing, you can answer queries quickly in logarithmic time. Remember, the previous version of the problem, it's a one-shot. There was no pre-processing. Pre-processing was a constant or zero. But the query time was linear, and that was terrible. If you only do it once, it's not so bad. But if you're going to do it over and over and over again, you don't want to have to do it from scratch every time. You want to pre-process, which amortizes all the work for all the queries, and then you can answer queries quickly. Right? That's why phone books are sorted by name. Think about it. It's an obvious statement, but it's also subtle. Somebody did the pre-processing, like the phone company. I don't even know if they use phone books. Have you actually seen a phone book in your life? Okay, good. We're not that far down yet, but paper books and things like that. But it's sorted by name. Why? Because you want to do queries quickly. So you want to look up something alphabetically, and when you look something up, you're doing a binary search. How many understand that? In a phone book or even in your own textbook. If you want to go to page number 175, you're doing a binary search on the page numbers. Otherwise, you'll be sitting there a whole lot, longer time to find page 175 by going 1, 2, 3, 4, 5. No, 170. No, okay, 6, 7, 8. No, that's not how you search a bill. Doing binary search because it's pre-processing already done for you. Okay, so let me say a caveat here. There's always kind of catches occasionally. Numerical precision here matters. When you start computing sines and cosines, and these points become real numbers, and inverse tangents to compute triangles and stuff. You don't have to do all that, but if you do, you have to realize that a point will be very close to a boundary or to a vertex, and because of numerical imprecision, you may get the wrong answer by a slight delta drift from the right answer because you're using real numbers. When you're doing everything on real numbers, errors tend to compound, and if you're not careful, they'll get away from you. How many understand that motif or notion? Okay, just be careful. There's a way to do computational geometry that avoids all of that. It's very tricky and esoteric, but there's ways to do it to completely avoid round-off errors and imprecision derived from arithmetic and real numbers. It's just a lot more overhead, and we won't get into it here. But I'm just bringing it to your attention so you don't rush ahead. And, just remember that mathematically, if you square the square root of 2, mathematically, what is the answer if you square the square root of 2? 2. Numerically on the computer, what is the answer? It's 1.9999995, whatever it is. Just keep that in mind. I know it's obvious when you hear it, but often you get snagged on it when you program in the large in real life. Now, just to finish this off, the wedge before there's a point inside created these wedges. Which point inside do we have to use to make all this system work, this whole algorithm work correctly? Which point inside did we use? The centroid. Do we have to use the centroid? No. Could we have used other points? Yes. Could we have used one of the vertices of the actual polygon as the point inside? Could we have used this point to create all these wedges?
Yes.
Obviously, yeah, that would work too. Now you're getting it. So don't even worry about centroid. Just pick one of the points of the exterior or the boundary and use that, and then you'll get pretty much the same algorithm, the same answer. Same polar angle, you sort it by polar angle. Do binary search on the angle of the interior point, and there you go. So you don't even have to find the centroid. I just want to bring it to your attention. Once you have an algorithm that's kind of reasonably general and interesting and robust, then you can make also the variations and get the exact centroid. Let me ask you another question. Could you use a point completely on the outside to do the slices? You could. It'll maybe complicate things a little bit, but you could still do that even. It doesn't even have to be inside this plane, creating the wedges. And next time we're going to generalize this to arbitrary non-convex polygons, and they'll get even more dicey. Okay, any last minute questions? All right, we'll see you around.
I had a question. Actually,
Yeah, sure. I can send you an email or if it have a good night.
that is my community called